This is Chapter 8, Wildland Fires. The objectives of Chapter 8 are to explain the basic combustion principles and be able to apply them to wildland fires and differentiate wildland fire behavior from structural fire behavior. To examine how weather conditions impact wildland fuels and behavior of wildland fires. To describe the various parts of wildland fire and identify how fire behavior impacts the methods of firefighting wildland fires, including some of the special techniques needed to extinguish and control these fires. To describe the method used to classify resources used on wildland fires and how fire behavior impacts the type and the amount of resources needed to suppress wildland fires. And finally, to describe the various resources and tools used in the extinguishment of wildland fires. There is a vast difference between wildland firefighting and structural firefighting. A careful study of these differences indicates variations in certain factors that impact fire behavior. However, all fires follow natural laws of physics, and once learned they can be applied to both firefighting arenas. Discussion in this chapter centers on the differences and similarities between both types of firefighting and how fire extinguishment methods differ as well. This chapter begins with an overview of the basic components of combustion. The fire tetrahedron is a new model used to depict the fire process. Despite being a valid model for fire extinguishment, the former triangle model is still used by most wildland agencies to explain combustion and extinguishment processes occurring in wildland fires. In wildland firefighting, the heat is cooled, the fuel is removed, or the oxygen is excluded from the fuel to stop the process of combustion. These actions are carried out by hose lines directing water at the heated fuel, or by hand tools or machines, which remove the fuel from the path of the heated fuel. Another technique is to use dirt or foam to smother, cool, and or exclude the oxygen. The fire triangle shows the wildland fire combustion process: fuel, heat, and oxygen. One side of the fire triangle is the heat side that represents its removal or reduction of the ignition temperature of the fuel. Once the fuel is cooled below the temperature at which it gives off vapors, combustion will no longer take place. In other words, the fire is extinguished. Water is the most effective fire extinguishing agent that is readily available. The key to using water is to use only the amount it takes to do the job. To do so, firefighters use a fine spray, breaking up the mass of the water so that the maximum amount of heat will be absorbed by as little water as possible. The conversion of water droplets into steam allows the water to absorb greater amounts of heat energy. For deep-seated fires in forest materials, a straight stream is needed to penetrate and cool the material below the ignition temperature. For fuel giving off large amounts of radiant heat, a straight stream may be needed to supply sufficient water to reach the fuel. On many wildland fires, water is not available in abundance. Therefore, other extinguishment means need to be used. For example, small amounts of water from a hose line or back pump are used to cool the fire so that firefighters can get close enough to the edge to then use tools to remove the burning fuel from the path of the fire. This action breaks the fuel side of the fire triangle. In the 1988 Yellowstone National Park fire, a compressed air foam system, CAFS, C-A-F-S, was used successfully in coating and protecting dwellings with a Class A foam. Compressed air foam systems inject air into the foam solution with an air compressor. The foam is made by mixing 1% to 3% of a foam solution with 10% water and compressed air. This method significantly reduces the amount of water needed, thus enhancing its application to wildland fires. Using foam and fire retardant materials, firefighters can slow a large fire. These materials can be applied by aircraft and special foam application equipped vehicles, such as the CAFs. Foam can be made wetter if needed for use on a hot advancing fire, or it can be made drier to adhere to vegetation. The foam provides a protective blanket from the fuel. The added detergent and the compressed air foam allows water to break the surface tension and penetrates fuels easier and more quickly. This table identifies the relationship between the foam expansion rate and the drain time. The wetter the foam is, the deeper it will penetrate. The drier the foam is, it will be lightweight and act as a protective covering. In wildland fire suppression, removing the fuel from the path of the fire is the most common method of extinguishment. These operations include cutting or scraping, using bulldozers or hand crews, or backfiring operations where the fuel is burned in front of the main fire, thus removing burnable fuel in the path of the main fire. Oxygen can be removed or excluded from the fuel on a wildland fire by throwing dirt directly at the base of the flames or in the area of combustion to cool it down and exclude the oxygen from the fire. This action is followed by other extinguishing actions to ensure that the fire is completely out and cannot spread to any unburnt fuel. If limited water is available, this method reduces the total amount of water needed, but generally the penetrating ability water is needed to extinguish any deep-seated fire. Aircrafts are used on wildland fires to drop either water or flame retardant solutions that are designed to suppress the combustion process by cooling and smothering the fuel. To be approved for use, the flame retardant material must degenerate or biodegrade, generally within 30 days of its application. Wildland fire heat output is transferred in the same ways as in a structural fire. The heat moves in 4 ways: conduction, convection, radiation, and direct flame impingement. We already know this, so this is a review, but in conduction, the transfer of heat is within the material itself. In convection, the transfer of heat is by liquid or gas. Radiation radiates energy ahead of the fire. Direct flame impingement, the flame front is moving upslope where the flames lay down or move at an angle to the slope. Direct flame impingement increases the burning rate as it not only preheats the fuel, but the flames also provide a direct source of ignition. This figure illustrates how a wildland fire can quickly move up a hill. On wildland fires, a 5-step decision-making process is applied to each of the following factors. Factors impacting life safety. Life safety concerns are those factors that may lead to death of civilians and or firefighters. Factors impacting property safety. Property safety is a concern because of the opportunity for rapid fire spread from a hot wildland fire into a structure, which may lead to a conflagration. Factors that may harm the environment. One factor that may harm the environment is a large loss of the soil after burning away the vegetation, as roots work to hold the soil in place. Without the roots to hold the soil in place, the vegetation is washed away during a rainy season. A second environmental issue is the toxic particulates and ash given off during the combustion of wildland fuels. Some smoke and ash material carry acids and other toxic materials, which can impact paint and persons who are sensitive to these types of materials. Factors that will harm wildlife. The loss of vegetation results in the loss of the food supply for many of the forest creatures. And the availability of needed firefighting resources. The non-availability of aircrafts and other resources can seriously hamper the efforts of firefighters as they attempt to control the fire in its early stages. Fire behavior is also affected by weather, topography, and fuels. These 3 main factors are often referred to as the fire behavior triangle. Each factor of the wildland behavior has subcomponents, which also affect the fire behavior. One method that firefighters and wildland management personnel use is the burning index, which is a number in an arithmetic scale determined from the fuel moisture content, wind speed, and other selected factors that affect burning conditions, and from which the ease of fire ignition and their probable behavior may be estimated. Understanding weather characteristics is essential for the safety and effective extinguishment of wildland fires. In basic fire chemistry, fuel temperature is a factor that is absolutely necessary to initiate and to continue the fire combustion process. Temperature is one component of weather that impacts the behavior of wildland fuels. The range of ignition temperature of woody fuels is between 400 and 700 degrees Fahrenheit. Normally, woody fuels will burst into flames approximately 540 degrees Fahrenheit. However, the time required to bring wood to this ignition temperature will vary with the amount of moisture in the fuel, as the heat must drive the water out of the fuel in order to bring it to this ignition temperature. The relationship between the vertical temperature distribution within an air mass and a vertically moving parcel of air is termed air stability and instability. If air mass temperature decreases sharply with altitude, conditions are favorable for air currents to rise vertically through the air mass. This movement produces an unstable condition, which is dangerous, as any movement of vertical and horizontal currents. At the same time, this creates an unpredictable wind situation. A temperature inversion occurs when cooler air is found close to the ground surface and warmer air is above the pool of cooler air. Quite often this occurs along the coast, where a marine inversion is created when cool, moist ocean air flows inland and settles in low areas. If a fire in this low area heats the cooler or lower lying air to a temperature that is greater than the warm air overlying the area, the heated air breaks through the inversion layer, resulting in a quick rush of cool air that causes the fire to accelerate and burn with a much greater intensity. Water vapor is simply water in a gaseous state and is an important ingredient in a fire's behavior. As air moves over the surface of water, it picks up water vapor. This process is called evaporation. The oceans are the primary source for adding water vapor to the atmosphere. Lakes, rivers, snow, vegetation furnish lesser amounts. Relative humidity is the ratio or the amount of water vapor in the air to the maximum amount than the air can hold. If relative humidity is 100%, the air is completely saturated. It can hold no more water. In contrast, if the relative humidity measures 50%, then the air is only half saturated and is able to hold 50% more water. Low relative humidity draws moisture from fuels, allowing them to heat more rapidly. When the relative humidity is below 30%, the fuel becomes very dry, and it makes conditions favorable for wildland fires. If the reading is 15% or below, the condition is declared a red flag alert. During red flag alerts, fire departments prepare for wildfires by moving and adding additional resources for initial fire responses. Wind is the result of uneven heating of the Earth's surface. Heating the air causes it to become lighter, therefore it rises, drawing in cooling air from below. Over the surface of the Earth, several major forces are at work unceasingly to stimulate air movement. There are vast areas of heating near the equator that are much closer to the sun, where the heat produces rising air currents that return to the Earth in cooler regions. This movement of warm air to cooler air sets up a circulation pattern of rising and descending air currents. The pattern is impacted by the Earth's revolutions, which deflect the rising air currents and cause them to move in a deflected horizontal direction. Foehn winds are gravity winds, which occur when air is pushed over high elevations and then flows downhill. Gravity winds also occur when a high-pressure system is located near mountain ranges, where the airflow around the high-pressure system causes some of the air to spill over to higher elevations, resulting in a strong wind moving downhill at high speed. As the Foehn wind blows down slope, it is compressed and becomes warmer and drier. This moment of warm air dries the fuels and reduces the fuel's moisture. During these conditions, winds can reach 70 miles per hour or higher. Generally, nighttime brings more moisture into the air as it's been cooled. This cooling effect from the moisture in the air affects the amount of moisture within the fuel. Nighttime or early morning provides firefighters with an opportunity to take action when the fuel moisture is higher. At other times, if all other conditions are conducive to wildland fire, fuel moisture does not make a difference. Dust devils and fire whirls are indicators of unstable surface conditions that will cause erratic fire behavior. These conditions are a result of uneven heating, which causes ground temperature to vary. Heated air rises and is pushed horizontally by prevailing wind. In some cases, it begins to whirl. The problem for firefighters is that these whirling winds throw burning materials ahead of the main front fire, creating fire spots. This is caused by fuel preheating and results in rapid fire spread. Slope affects the spread of fire in two ways. First, the fuel is preheated by direct flame impingement and convective air currents. The second, a draft is created. A fire will run faster uphill than it will downhill, as long as the wind is not strong enough to change the direction of spread. The direction a slope faces to the sun is called the aspect or exposure. This impacts the spread of fire in several ways. South-facing slopes are exposed to more radiant heat by the sun, resulting in temperatures that are normally higher, with lower humidity. The fuels are usually heated more, and as a result are dry. The warming changes hourly as the sun moves across the sky, resulting in different fire behavior that is affected by the angle of the sun and the heating of the fuels. Fire behavior is affected by elevation as well. It influences how the air moves from the valleys that are warming to the cooler ridges. Also, elevation can affect positioning of a warm or cool air mass in thermal belts. It also affects the length of the fire season, as light flash fuels are drier and quick burning. Elevation also affects fuel types. The topography of land affects wind patterns and fire spread. Canyons, saddles, and ridges directly influence how a fire burns. Wide canyons will have little effect on the wind pattern, while narrow canyons may significantly impact the wind as it's driven down the canyon. Narrow canyons with steep walls are locations where fire can jump across by radiant or convective spotting due to the short distances involved. These canyons are extremely dangerous for firefighters, as a fire can easily cross over the canyon and get behind the working fire crews. Saddles are the low topography between two high points. They are the point of least resistance for wind and wind eddies. They provide the potential for rapid rates of fire spread because fires are pushed through saddles faster during unsloped fire runs. Saddles are not used as a safety zone. Ridges may not only divide the terrain, but they also have different wind conditions on each side. This is especially true along coastal regions, where weather patterns are changing due to the temperature difference between cooler air from the ocean and warmer air from the heated land areas. Steep, narrow draws in canyons are called chimneys. Radiant or convective heat can occur across narrow canyons due to the short distances involved. They draw fire up in them in the same fashion as a flue draws heat up the chimney for a fireplace. A fire burning on level ground, or up to 5% slope, will spread twice as fast when it reaches a 30% slope. The rate of fire spread will double again as the slope reaches 55%. As you get higher in elevation, the vegetation changes. Different altitude equals different fuel types. Understanding and identifying the type of fuels is critical to firefighter operations and safety. The amount of fuel available to burn in any given area is called fuel loading. Grass and other small plants that are found on the forest floor are light fuels. Medium fuels consist of brush that is 6 foot in height or lower, growing in fairly thick stands. Fires in the heavier fuels produce more BTUs, and as a result are more resistant to fire suppression activities. They require more water to cool, extinguish, and to control them. They consist of brush taller than 6 feet, timber, and hardwood trees. A fuel shape may determine how the fuel can affect the ignition spread of a fire. The smaller fuel, the faster it will preheat, ignite, and spread. The larger fuel, the more BTUs it will produce. Fuels that grow and spread from the ground surface to higher vegetation are called ladder fuels. Ladder fuels support fire spread from the ground area into higher or taller vegetation, whereas aerial fuels include all green and dead materials located at the upper forest canopy. The main aerial fuel components are tree branches, crowns, moss, and high brush. Aerial fuels can provide a path for the fire to travel in the higher fuels. These fires are inaccessible and as a result are difficult to extinguish. These fires travel through the top of the trees independent of the ground surface fire. These are called crown fires. The amount of moisture in the fuel will affect how easily it will ignite and how intensely it will burn. The moisture content of fuel is classified in 2 ways. One is dead fuel moisture, which the content of the moisture in the fuel is not living. The second is live fuel moisture. The live fuel moisture is the amount of fuel moisture in the living, growing fuels, which gain moisture primarily from the plant root system. Dead fuel moisture is changed only by the moisture content of the air. Both are measured as a percentage of the weight of the fuel. The time lag is the time it takes for the moisture content of the fuel in the surrounding air to equalize. Time lag is expressed as a rate, usually in hours. The warmer the fuel, the less heat is required to ignite it. This is particularly important when dealing with light fuels. Their small size and mass allow them to heat up more quickly and change their moisture content faster. Wildland fires are identified by a left flank, which is the left side of the fire, and a right flank, which is the right side of the fire. These sides are identified the way you would look at them if you were looking at it from a map. The head of the fire is the outmost portion of the fire that is moving from the rear. The anchor point is a location near the origin of the fire from where it is safe to start working. Areas inside the fire that have not been burnt out yet are called islands. If an area has not been burned on the perimeter, it's called a pocket. It is surrounded on one side by a finger. The rear is the point of origin in most fires. This illustration identifies critical parts of wildland fires. Also note up top the spot fires and hot spots. Those are over and near the fire line. Firefighters will always find a safe working area, either using the anchor point or a safe location from which they start working on the fire line. The occurrence of spot fires depends on the topography and the weather factors, as well as the character of the fuels in the main fire. Spotting occurs when wind and convection columns thermally produce a column of gas, smoke, and debris produced by a fire. Broadcast hot fire brands into unburned fuel ahead of the main fire. Crown fires, with their intense heat and strong convection currents, frequently start spot fires. They can throw burning embers far ahead of the main fire front. Very large fires can become so large that the combustion process creates its own indraft of oxygen, which increases and serves to continue the combustion process. Firefighters use this principle to backfire or burn out the fuel near the fire edge in an effort to separate the fire from the fuel. This fire extinguishment method works well when the backfire is ignited to become entrained into the main fire, thus removing the fuel in the path of the main fire. Area ignition is an event that happens when spot fires occur in an area with unburned vegetation, or when the spot fires are burning in a bowl or in a canyon, or in an area where heat from the spot fires is trapped. In some cases, an inversion layer will hold the heated gases within the bowl. The spot fires that are burning preheat the unburned vegetation to a point where it reaches its ignition temperature. All at once, the preheated vegetation in the area explodes into a combustion. If firefighters are in the bowl area, the chances of survival are slim. Similar conditions exist in a confined room where flashover occurs, resulting in the entire room exploding in a fire. Engine company, water tenders, hand crews, aircrafts, and bulldozers are used for wildland fires. Using NIMS in the command section, all of these resources are placed into a classification system based on their design, capability, and inventory of equipment carried. By using standardized classification systems, all agencies can quickly identify the type of equipment they are requesting from another agency or sending to another agency. This system standardized the way resources are classified in the United States, allowing all agencies to understand the capability, design, and standard required equipment. The typing of all resources used in wildland fires is available in a field operations guide. The system classifies the units into strike teams and task force. A strike team is a set number of resources of the same type, with minimum staffing levels. Engine strike teams include 5 engines and a strike team leader, normally in a separate vehicle for mobility and communications. A task force is any grouping of resources with a task force leader assembled on a temporary basis for a specific mission. A task force can be any size, including a variety of resources. The engines within a strike team or task force are identified based on their capabilities by a classification system that puts them into types. The various engine types are not supposed to be mixed on strike teams. However, if they are in a strike team configuration, the team takes the classification of the least capable unit. Of the various types of apparatus, both air and ground, the fire engine is the most versatile. It can fight fire both day and night and is not restricted by visibility, as is the case with aircraft. It can deliver water to a fire at various capacities and transport crew to a fire with their equipment. Its crew can construct a hand line, and the unit can be used to fight structural, vehicle, or other types of fires. On any sizable wildland fire, the biggest portion of suppression personnel will consist of hand crews. A hand crew is simply a group of firefighters that's formed into a suppression team. They use hand tools and power tools to reduce the fuel side of the fire triangle. Hand crews usually contain from 12 to 25 firefighters who are assigned to actively suppress low-flame production fires and to construct hand lines along the fire's edge or ahead of the fire for future holding action or for backfiring. These crews often get the toughest assignments, as they can go to locations where vehicles, including bulldozers, are unable to travel. A strike team of hand crews consists of a strike team leader with 2 or more supervisors and up to 40 crew members, all of the same type. The kind of fire line work that can be performed by the crew is based on the type of crew. There are 2 classifications of hand crews. Type 1, these are highly trained persons able to work on all fires directly on the fire line. In Type 2, these persons have some training with fire line work restrictions. Hand crews can work with engine companies assisting in bringing hose line or assist a bulldozer by following and picking up any fire missed by the bulldozer blade. Hand crews also need to perform cold trailing to make sure the fire is completely out. The use of bulldozers in conjunction with other ground components provides for a tactically balanced and integrated fire suppression force. Bulldozers attack the fuel side of the triangle. A strike team of bulldozers is defined as containing 2 dozers, 2 operators, 2 swampers, and a strike team leader. A swamper is a worker on a bulldozer crew who pulls the winch line, helps maintain the equipment, and generally assists with suppression work on a fire. Bulldozers are typed into three broad classifications. Type 1 is a D7, D8, or D9, heavy, thick brush, timber, or road construction. Type 2 bulldozer, medium, D6, and D11 are heavy to medium brush. Type 3, light, D4 and D6. These are for light fuels, grass, and fast-moving fire. Bulldozers are effective in removing fuels along the fire line. They do their best work during direct fire attack by cutting the fire line on a fire flanks. On indirect attack, they can be used to cut brush lines, escape routes, or safety zones in front of the main fire line. They also are used to open up roads and other access points in wildland areas. Bulldozers are often used to cut water bars to ensure that the soil is trapped rather than washed off the side of the hill during the rainy season. Both fixed-wing and rotary aircraft will attack the heat leg of the fire triangle, cooling with water or retardants. Aircrafts are typed on the ability to carry water or fire retardant materials. Some are designed to drop materials in a single drop or spread it out by dropping a load from their tanks in a series, thus spreading it over a larger area. Fixed-wing aircraft can drop retardant or water on the head in front of a hot, fast-moving fire to slow it down and allow engine companies, hand crews, or bulldozers to work the flanks and eventually catch the head once it's cooled and moving slower. In addition to slowing a fire, aircraft can paint the fire line with fire retardant to slow the fire front or confine it within a specific area. Because they can carry much more retardant than a rotary aircraft, the fixed-wing aircraft can cover a larger area, which helps reduces the total heat buildup and allows access for ground crews. There are 4 classification types of fixed-wing aircraft. A Type 1 is capable of carrying 3,000 plus gallons. A Type 2 is capable of carrying 1,800 to 2,999 gallons. A Type 3 is capable of carrying 600 to 1,799 gallons. And finally, Type 4 is capable of carrying 100 to 599 gallons. The principal advantage of a helicopter is its ability to operate from locations close to and on the fire line. Its ability to take off vertically and land in close quarters makes it a valuable tool for close support action for ground-based and other aerial operations. Various attachments that are available also permit helicopters to perform certain jobs that would be difficult, if not impossible, by any other means. Rotary-wing aircrafts cannot carry as much as fixed-winged aircrafts, but they can work closer to houses and pinpoint the application of the retardant more precisely. Nevertheless, both fixed and rotary-wing aircrafts are needed, as each unit fulfills an important but different fire protection function. Helicopters may also be used for application of liquids such as water or retardant chemicals over key fire line targets. Because of their ability to hover, they can be directed precisely via radio communications with ground personnel. In addition, helicopters can be useful in transporting injured firefighters and burn victims who will be flown out to predetermined hospital burn wards. Helicopters have often served dramatically to evacuate persons stranded or threatened by fire. Like fixed-wing aircraft, rotary-wing aircraft are broken down into 4 types. A Type 1 is capable of carrying 16 people and 5,000 pounds with 700 gallons of water or retardant. A Type 2 has 9 to 15 seats, capable of carrying 2,500 to 4,999 pounds, and capable of carrying 300 to 699 gallons of water or retardant. A Type 3 has 5 to 8 seats, capable of carrying 1,200 to 2,499 pounds, and 100 to 299 gallons of water or retardant. And finally, Type 4 has 3 to 4 seats and carry 600 to 1,199 pounds, and capable of carrying 75 to 99 gallons of water or retardant. The direct method of attack is where the attack itself is directed on the edge of the burning fire. Some ways to accomplish the direct method of attack are by water, chemical agents and retardants, or cooling, separating the main fire from the available fuel. For example, the water can be sprayed directly on the burning edge of the fire, or a fire can be set to burn out the fuel in advance of the main fire. This method of attack has some tactical advantages and disadvantages for firefighters. One tactical advantage is that firefighters are working directly on the line, and the actions result in the fire being controlled at the location where the attack is occurring. The line being cut around the fire must be continuous and complete, enough to hold the fire to the burning side of the line. If successful, a direct attack limits the fire from building momentum and eliminates the need for backfiring or firing out to burn out the fuel between the main fire line and the line being constructed for fire control. It is generally used in the initial attack phase and used on the flanks or head of the fire depending on the amount of heat being generated. The main objective of this attack method is to stop the spread of fire as soon as possible. Another advantage of the direct attack is that it holds the fire to a minimum acreage by taking advantage of the line portions that have not burned due to the lack of fuel or poor burning conditions. Other positive aspects include the fire being controlled more quickly with less loss of wildland resources than a backfire would require, and firefighters are able to use the black area to escape if necessary. The disadvantages of the direct attack are that it may not be effective against an intensely hot or fast-moving fire, and because this attack is risky, it requires close coordination of all crews. Generally, the incident commander makes this determination based on the flame length of the fuel, the topography, and the weather conditions. Because the fire line follows the burning fuel, it generally is longer in length and is irregular as it follows the edge of the fire, which causes a longer fire line. Another concern is that firefighters are working directly on the fire line, so they are exposed to more heat and smoke while working on the fire. They can accidentally spread burning materials across the fire line. Because the direct attack follows the fire line, it does not take advantage of barriers such as rock, outcroppings, lakes, rivers, and other barriers. Finally, there is usually more cleanup and patrol work needed to be accomplished, and crews must carefully follow behind to ensure a complete extinguishment. The indirect attack method consists of fighting a wildland fire by constructing control lines or by backfiring the fuel out at a distance ahead of the main fire. It is used when the fire is burning too hot or too rapidly to employ direct attack methods, or when insufficient fire suppression forces are available. Because the indirect method is used on hot, intense fires, it is the choice most often selected on large fires. A pre-constructed fire line is put ahead of the fire and is held in place by ground and air forces. If it can be held, it becomes the final control line. Pre-constructed lines can be reinforced with retardant drops to cool the fire as it approaches the line, or can be protected with a backfire. A backfire is used to set the fuel on fire in front of the main fire to deprive the main fire of fuel. A successful backfire stops the forward advance of the fire when the fuel in front has been removed. Advantages of the indirect attack method are constructed control lines can be located using favorable topography. This line can often be completed with fewer suppression resources. In most situations, the total amount of fire line cut is shorter. Another important aspect is firefighters can work away from the large amounts of heat and smoke and thus reduce their fatigue. The disadvantages are that fire is not being extinguished during the time the control lines are being put in place, and during this period additional fuel is being consumed. Also, any areas that are not burning are included in the control line perimeter, so advantage is not taken of these lighter fuel areas, and in some situations unburnt fuel is left inside the control line. Further, it places firefighters in an area where burning out or backfiring is in progress. In some cases, secondary lines may need to be cut or burned out, requiring more work and exposing firefighters to additional danger. The combination attack takes advantages of the direct attack and the indirect methods when possible. Firefighters will work directly on the fire line in those areas that are safe and can be reached quickly in an effort to contain as much of the fire as possible. At the same time, resources permitting, crews begin to work indirectly in those areas where fire line cannot be attacked directly. Most incident commanders will use this method of attack. There is not one single method of fire attack that must be followed throughout the fire suppression steps. Many times a combination of two or more methods is used, or in some situations all methods will be used simultaneously. A tandem attack is a direct attack method with the attacking forces working in tandem, which means one unit following the other. A pincer action may be conducted on any size fire. However, it is most often used on small fires. The objective of a pincer action is to move crews along both flanks of the fire to a point where the flanking forces move closer together in a pincing action near the head of the fire. Resources include hand crews, bulldozers, engines, aircrafts, or a combination of these. An envelopment action involves taking a suppression action on a fire at many points in many directions simultaneously. It provides for a rapid attack and, if coordinated properly, can be highly effective on smaller fires. This attack method requires a large amount of suppression forces to be committed to both flanks of the fire, and close command and control must be established. Units taking part in this type of action should be experienced and aggressive. Another method of attack is the parallel method. This method of suppression, in which a fire line is constructed approximately parallel to and just far enough from the fire's edge to enable personnel and equipment to work effectively. In summary, for wildland fires, the original fire triangle model is applied rather than the newer fire tetrahedron model, as the fire triangle is used to explain both the combustion and extinguishment process on wildland fires. Although wildland fires are similar to structure fires because they have the same fire combustion principles, certain factors will influence the differences in the fire behavior. Structural fire behavior is impacted by the confinement of the combustion process within an enclosure. Wildland fires are outside fires where the weather, fuel, and topography affect the fire behavior. Each of these components affects fire behavior, and under certain circumstances, a combination of conditions in one or all can result in serious fire behavior. The three methods of attack used on a wildland fire are direct, indirect, and a combination attack. The type of attack depends on the fuel, weather, and topography, as well as the type and availability of firefighting resources. Each attack method has its advantages and disadvantages. Other configurations of attack methods are pincer, flanking, and development. And this concludes Chapter 8, Wildland Fires. Thank you.